Hello, everyone. Thank you, as always, for coming to CHAMP. I am excited to introduce this week's speaker. Alapan from the University of Michigan will tell us about Frobenius-Poincaré function and Hilbert-Kunz multiplicity. Alapan.
Yeah, thanks for the introduction, and thanks for also giving me the opportunity to speak here. So as my title suggests, I'm going to talk about Frobenius-Poincaré functions and Hilbert-Kunz multiplicity. So what are Frobenius-Poincaré functions in one sentence? So it's the generalization of Hilbert-Kunz multiplicity when the underlying structures are graded. So I'll start by recalling what Hilbert-Kunz multiplicities are and why perhaps those are important. So what is Hilbert-Kunz multiplicity? So let's see. So it's a multiplicity theory in positive characteristic. So our setup is this. So fix a Noetherian ring S and a finite colength ideal J inside S. So by finite colength, I just mean that the length of S mod J is finite. So Monsky has shown the following. So if you look at this quantity, the length of S mod J power P power N, I will explain what I mean by J power P power N. So this grows as a constant times P power N power dimension of S, and then the rest will grow much more slowly. So it's the P power N power dimension of S minus 1. So what do I mean by J power P power N? So J power P power N is just the ideal generated by F power P power N. So it's, let me write it in words. Generated by F power P power N, where F is in this ideal J. Okay, so let's look back at this result, Monsky's result again. So it says that if I look at the length of S mod J power bracket P power N, it goes as some constant C, and then term of the order P power N power dimension of S, and then lower order terms. And this C is called the Hilbert-Kunz multiplicity of the pair S comma J. So C is the Hilbert-Kunz multiplicity. Sorry, my handwriting is awful. Multiplicity of the pair S comma J. So said in other words, the C is basically the limit as n goes to infinity of length of S mod J power P power N, and then normalized by P power 1 divided by P power N dimension of S. Okay, now you might ask why these numbers are important. So examples and results suggest that this is, so just looking at this association, sending the pair S comma J to the C, which I will denote by EHK S comma J. This defines a multiplicity theory in positive characteristic. So what do I mean by that? So what's the role of a multiplicity theory? It should detect some notion of singularity, right? And how does Hilbert-Kunz multiplicity detect notions of singularities? So if I take, so let's see, so this EHKSJ detects singularities of the pair S comma J. So what do I mean by that? I'll just go to the next page. So for example, when S is regular local and my ideal J is the maximal ideal, then the Hilbert-Kunz multiplicity of S comma J is 1. And in general, if I take a local ring and any ideal in that local, finite colon ideal in that local ring, the Hilbert-Kunz multiplicity is always greater than 1. In general, the Hilbert-Kunz multiplicity of S comma J is always greater than 1. And the understanding is this: the higher the Hilbert-Kunz multiplicity, the worse the singularity is. Okay, so let me just make a precise statement that makes this vague statement much more clearer. The vague statement that higher the Hilbert-Kunz multiplicity is, the worse the singularity is, much more clearer. So what's the result? So this is a theorem due to Blickel and Enescu. So roughly it says the following. It says that if the Hilbert-Kunz multiplicity is close enough to 1, then the ring has to be Cohen-Macaulay and something called F rational, which are thought to have better singularities. So what's the result precisely? So I'm not stating the result in the most generality. I'll just state it in the form which is much more understandable. Okay, so Blickel and Enescu result says the following. So let R be a Noetherian local ring of positive characteristic. So assume that R is a complete domain. So suppose the characteristic is P. So if the Hilbert-Kunz multiplicity of the ring with respect to its maximal ideal, if that is less than equal to 1 plus maximum of 1 divided by ER, where ER is the Hilbert-Samuel multiplicity, and then the other term is just dimension of R factorial, then first of all, Rm is Cohen-Macaulay. And second, R is F rational. So what is F rational? F rational is an analog of rational singularities in positive characteristic. So precisely, a ring is called F rational if the ideal generated by a system of parameters of the local ring is tightly closed. But let me not get into the details of that. Yeah. So again, so let me remind you of the theme of the underlying point of this theorem. It says that if I start with a local Noetherian local ring, and if the Hilbert-Kunz multiplicity is close enough to 1 in a precise sense, then the ring has mild singularities in a precise sense. And it basically says that higher the Hilbert-Kunz multiplicity, worse the singularities. Okay, but the main point of discussion of today's talk is Hilbert-Kunz multiplicity when the underlying structures are graded. So, and the main object is what I call the Frobenius-Poincaré functions. So the usual Hilbert-Kunz multiplicity, it associates a number to a pair, and instead of associating a number, I will associate a holomorphic function to a pair when the pairs are graded. So I'm going to talk about Frobenius-Poincaré functions now. Frobenius-Poincaré. Okay, let me just write it in full words. Frobenius-Poincaré functions. Again, let me just write down whatever I said verbally. So given Noetherian graded K algebra, I'll be precise what I mean by this. R and a finite colength homogeneous ideal I. So the Frobenius-Poincaré function is a holomorphic function F. And how does it relate to the usual Hilbert-Kunz multiplicity? So the value of this holomorphic function at 0 is the Hilbert-Kunz multiplicity of this pair R comma I. Okay, so this is a very rough overview of what Frobenius-Poincaré functions are. Now I'm going to tell you what Frobenius-Poincaré functions are precisely. Okay, so just to motivate the definition, I will just I'll choose a concrete setup. So what is my concrete setup? So I haven't yet told you what do I mean by a Noetherian graded K algebra is, but I'll do that probably in a second. So I'm trying to motivate the definition of Frobenius-Poincaré functions now. So start with so R is a Noetherian n-graded domain. Okay, so and fix a finite colength homogeneous ideal. I is finite colength homogeneous ideal. So if you look at the ring R power 1 by P power n, so this is basically the collection of all P power nth roots of elements of R. So this has a natural, 1 by P power n grading. Right. So if we look at the following object, which is R power 1 by P power n and then mod I times R power 1 by P power n. So by this, I just mean the extension of I into this ring. So this also has a natural 1 by P power n grading. So I can look at its Hilbert series. But when I take the Hilbert series, I also allow for the rational powers of the variable t. So take Hilbert series. So what is so how does it look like? So the Hilbert series looks like summation length of R power 1 by P power n mod I extended to R power 1 by P power n. And in the variable t, so if I look at the j by P power nth graded piece, the corresponding power of t is j by P power n. So it's not the usual Hilbert series, but I allow for roots of the variable t, and the sum is over j. Okay, so now I want to study this Hilbert series as a holomorphic function. So if I want to do that as a holomorphic function in the variable t, so if I want to do that, so I have to take P power nth root of the variable t, which is not possible in a holomorphic fashion. So for that, I make a change of variable. I'll just go to the next page and explain that. Right, so I start here. So replace. So this is not the best way of doing it, sorry. Start here. So replace t by e power minus iy, where y is the variable. So why do I do this? So now if I want to talk about t power 1 by P power n, that becomes just taking e power minus iy divided by P power n. So if I want to take the root function as a holomorphic function, I have to take a branch of logarithm and stuff. So if I make this change of variable, I can just take the P power nth root very naturally. in a holomorphic fashion. Okay, so if I make this change of variable, what do I end up getting? So I end up getting the following function. So it's length of r power 1 by p power n divided by r 1 by p power n, the j by p power nth graded piece, and this e power minus iyj by p power n. Sorry, let me just write it properly rather. Minus iy by p power n power j. Okay, and what's the theorem now? The theorem is that, so you can look at, so this gives you a sequence of functions, right? So this gives you a sequence of functions in the variable y. So the dependence on n is here. So if I look at the sequence of function and normalize it appropriately, then the theorem is that this sequence of functions actually converges to a holomorphic function. So let me write it down precisely. The sequence of functions, so this 1 by p power n dimension of r, and then summation length of r power 1 by p power n, I r power 1 by p power n, j by p power n, e power minus iyj by p power n, sorry, converges to first, so there are two statements. So the first that it converges for every y, for every complex number y. And the second statement, so now if I look at the limiting function, that's a function in the complex variable y, and the second statement says that the limiting function is actually holomorphic everywhere on the complex plane. The limiting function is holomorphic everywhere on the complex plane C. Okay, so let's just pause for a second and look back. So we started with this n-graded ring, and then looked at the collection of p power nth roots, and then formed a sequence of Hilbert series, and then made an appropriate change of variables so that we can talk about this function in a holomorphic fashion. So that was a very natural construction. And my theorem is saying that if I look at the growth of these functions, the limiting function is in fact a holomorphic function. That's the gist of whatever I did. Okay, and this limiting function is basically what I call the Frobenius-Poincaré function of the pair r comma I. Okay, and I will go to the next page and introduce Frobenius-Poincaré functions once more, but in this case for a module, graded module over a graded ring. Okay, so I'm going to give you a clear statement. So just note the following thing. So if the underlying field is perfect, which actually I will assume throughout. I will assume that underlying field is in fact algebraically closed, just to avoid any unnecessary complication. If the underlying field is perfect, then if I look at length, this object r power 1 by p power n, then I extended to I power p power 1 by n. This is just isomorphic to r I power 1 by p power n r. Okay, and with this identification, I will just restate my theorem in the setting I want to discuss. So what's the theorem? So let R be again be a Noetherian graded ring. By graded, I mean n-graded. And I homogeneous ideal such that length of R mod I is finite. Okay, so probably I'm just being very precise here. So Noetherian graded ring such that the degree 0 piece is the field K, is the field which is algebraically closed. So I'm starting with a Noetherian graded ring whose degree 0 is an algebraically closed positive characteristic field. Then, and also start with a finitely generated Z-graded R module. So let M be a finitely generated Z-graded R module. Then, number 1 by p power n dimension of M, length of M mod I power p power n M. So this is basically the analog in the module case of whatever I wrote down earlier. A jth graded piece e power minus Iyj by p power n, the sum is over j, converges for every complex number y. The second statement, the limiting function, which I denote by fmri, is holomorphic on the complex plane C. And I call this function fmri to be the Frobenius-Poincaré function of the triplet m, r, I. Okay, so I'll pause here, and if you have any questions about the definition, I'll take that. So the definition is a bit mouthful. So yeah, but I mean, although it looks a bit scary, but recall that it's just, remember that it's just a limit of Hilbert functions. Okay, and right away, note that if I plug in y equal to 0, so I get everything here is just 1, and I end up getting the, and if I take limit, I end up getting the Hilbert-Kunz, the usual Hilbert-Kunz multiplicity. So note that if I take the Frobenius-Poincaré function and evaluate it at 0, I end up getting the Hilbert-Kunz multiplicity of the module of this triplet, although I haven't defined what it is for a module. It's the exactly analogous definition. Okay, so now I guess a natural question here to ask is that why introduce this function, right? So you already have the Hilbert-Kunz multiplicity. I mean, what's the question? The question is, if I fix r, I, does the whether the Frobenius-Poincaré function carry more information than the Hilbert-Kunz multiplicity itself? And the answer is yes. So the answer is yes in the following sense. So even when R is polynomial ring, R is a polynomial ring. So there are ideals I and j such that the Hilbert-Kunz multiplicity of r, I and r, j are the same, but the Frobenius-Poincaré functions are different. Okay, so now I'm going to pose a vague question that we'll keep in mind for the rest of the talk and revisit it multiple times. So what's the question? So let's think for a second. So what is Frobenius-Poincaré function? So it's essentially determined by the information of the ring and the ideal and the Frobenius map. So which is in some sense a finite amount of information, right? And from there, I'm constructing a holomorphic function, and holomorphic functions are not just some random functions. Those are pretty rigid. For example, you have this Cauchy integral formula. If you know the value of a holomorphic function on the boundary of your disk, you know its value everywhere on the disk. So these are pretty rigid functions. So it's expected that the Frobenius-Poincaré functions, which are determined by some finite amount of information, will reveal this finiteness in its structure, right? And we want to understand we want to understand whether Frobenius-Poincare functions have special structures and properties. Okay, so the question is this. So this is a vague question. So do Frobenius-Poincare functions have special structures? I'm not going to answer this question right now, even I actually do not know the answer, but we will see examples that indicates that yes, it might have actually special structures, and that is kind of expected. Okay, so after posing this question, let's look at some examples, some simple examples. So first simple example is the case of a polynomial ring in one variable. So examples. So my R is just polynomial ring in one variable, and my ideal I is just the ideal generated by X. And what's the grading on this polynomial ring is the usual grading. Okay, so I want to compute the Frobenius-Poincare function. So what is it? So it's just recall the definition. It's just limit as n goes to infinity of the length of kx mod x power p power n, the jth graded piece, and then e power minus iyj by p power n, and j, the sum is over j. So if I look at this object, it has elements in degree till p power n minus 1. Sorry, I have missed this 1 by p power n normalization. So this is just limit as n goes to infinity. So wherever it's non-zero, the length is just 1. So this sum is just 1 by p power n, sum over j, e power minus iyj by p power n, having 1 factor here. And the sum is from 0 to p power n minus 1. So this is a geometric series. I can add it up, and I'll just get limit as n goes to infinity, 1 minus e power minus iy by p power n. So the common factor is e power minus iy by p power n, power p power n, and 1 minus e power minus iy by p power n. Okay, and if I take the limit, I mean, you can just calculate the limit. The limit is just 1 divided by e power minus iy divided by iy. Okay, so this is for polynomial ring in one variable. You can just try to use this calculation to make computation for polynomial ring in more than one variable. And so I'll just write down the result. So if I take polynomial ring in d variables, x1, x2, xd, and if my ideal I is x1, x2, xd, the maximal ideal with the usual grading, the Frobenius-Poincare function r comma I, so it's just 1 minus e power minus iy divided by iy power d. Okay, so I want to compute few more examples. So on the way, I'm going to mention first few properties of Frobenius-Poincare functions in general, and that will allow me to compute few more examples. Okay, so Frobenius-Poincare functions have properties which are analogous with. So in general, if I have a multiplicity theory, the multiplicity theory will have some general formulas. For example, it will be additive over short exact sequences. Then it will localize well and stuff. And Frobenius-Poincare functions have similar properties. So I'll just mention those properties. Properties of Frobenius-Poincare functions. Again, my setup is that R is a graded ring and I is a finite full-length homogeneous ideal. So take a triple m comma r comma I. So m is a finitely generated z-graded module over R. So let P1, P2, PR be the minimal primes of dimension equal to dimension of M in support of M. So look at the support of M and then pick the minimal primes of maximal dimension. Then the Frobenius-Poincare function of M, R, I is same as summation. So basically it says that you can recover the Frobenius-Poincare function of M from the minimal primes of maximal dimension in its support. So it's the sum of the Frobenius-Poincare functions of R mod this prime ideals Pj. I expanded to R mod Pj. And there will be some multiplicity here. The multiplicity is basically the length of M localized at Pj as an R localized at Pj module. So sum is over J. Yeah, so in a way, it says that if I understand Frobenius-Poincare functions for domains, I understand Frobenius-Poincare functions for all modules. And the second statement is the following. So I call this theorem localization formula. And the second property I called additivity. What does it say? Suppose that you have a short exact sequence of graded modules. Short exact of graded modules. So if dimension of M prime, so there are three statements, is less than dimension of M, then the Frobenius-Poincare function for M, I'm not writing all the parameters here, is same as the Frobenius-Poincare function for M double prime. So if the dimension of M double prime is less than dimension of M, then the Frobenius-Poincare function of M is same as the Frobenius-Poincare function of M prime. And the third thing, C, if dimension of M prime is same as dimension of M double prime is same as dimension of M, then the Frobenius-Poincare function of M is same as the Frobenius-Poincare function of M prime, the Frobenius-Poincare function of M double prime. Okay, so these are some trivial properties. And if I use these two properties, I can show the following two computations. The first one is this. So I can compute the Frobenius-Poincare function when the ideal is generated by a homogeneous system of parameters. So again, let's call it a proposition. So suppose that I is generated by F1, F2, Fd, where my D is dimension of R. R is underlying graded ring. And degree of Fi is delta I. So this is basically saying that this F1, F2, Fd will form a homogeneous system of parameter. Then the Frobenius-Poincare function of R, I, it's just ER. I will explain what this ER is. It's Hilbert-Samuel multiplicity in a sense. And 1 minus IY delta 1, 1 minus IY delta 2 till 1 minus IY delta D divided by IY power D. So basically the Frobenius-Poincare function sees the degree of this homogeneous system of parameters. And what is my ER? My ER is just limit as n goes to infinity 1 by n power d So for example, when R is standard graded, this is basically the Hilbert-Samuel multiplicity. So this is equal to the Hilbert-Samuel multiplicity when R is standard graded. Sorry, I missed a d factorial factor. Okay, so yeah, so the Frobenius-Poincare function contains the information of the Hilbert-Samuel multiplicity. It contains information about the degree of these elements, and it also understands the dimension. The next result is when R is one dimensional. You can explicitly write down the Frobenius-Poincare function. So if dimension, so suppose that, so this is the next proposition. So suppose R is one dimensional graded domain, and start with a finite colength ideal, I homogeneous, such that the colength of I is finite. Then the Frobenius-Poincare function is again ER times 1 minus e power minus IYH divided by IY. And what is H? H is the smallest degree of a non-zero element in the ideal I. Okay, and ER is defined in a similar way as before. Okay, so in all of these examples, note that the Frobenius-Poincare function has the following form. So it's a polynomial in e power minus IY, and then the denominator is just a power of IY. And so it's natural to ask the following question. So previously we were wondering whether Frobenius-Poincare function has special structures and forms, and all the examples show that they have special structures, although the examples are a bit handful. So I pose the following question. So are Frobenius-Poincare functions always of the form a polynomial in e power minus IY R divided by IY power dimension of R for some real number R. Okay, so I do not know the answer of this question. Okay, so so far I have said that this question has positive answer in the polynomial ring case when the ring has dimension 1 or the ideal is generated by homogeneous system of parameter. There is one more element to this list. So when the ring is two-dimensional, then the Frobenius-Poincare function also has this form. So I will come to the description of Frobenius-Poincare function of two-dimensional rings later. Okay, so now I want to switch gears and I want to move to different description of Frobenius-Poincare functions. The point is that so Frobenius-Poincare functions are defined over graded structures, and so we can try to exploit that there is an underlying graded structure, and if we try to understand from that point of view, we can show that the Frobenius-Poincare functions can be described in terms of the graded Betti numbers of the sequence of modules R mod I power bracket P power n. So what's the precise statement? So the precise statement is this. So let me define one quantity that will come up. So for graded finitely generated graded R modules, or finitely generated graded R modules Mn. So define chi R Mnt to be just the alternating sum of the Hilbert series of the store modules. If you look at the store modules, these are graded objects. You can look at its Hilbert series and then take the alternating sum of the Hilbert series. Okay, and the theorem is this. So r comma I as before. So choose a graded Noether normalization of R. Be a graded Noether normalization. Then the Frobenius-Poincaré function of if r comma I y is just limit as n goes to infinity of chi s. So my base ring is now the graded Noether normalization of r mod I power p power n, and k was my base field, evaluated at e power minus iy by p power n divided by iy power dimension of R. Okay, so if you look at this theorem, so it's saying several things. So first of all, if you look at the numerator, the numerator basically can be described in terms of, so if I fix the n and if I look at this quantity, this is basically containing the information of the graded Betti numbers of R mod I power p power n. That's one thing. And the second thing, it's saying that if you look at this sequence of functions, this sequence of functions is actually converging, and the limiting function is actually holomorphic. So it's part of, it's a consequence of the main theorem I stated at the beginning, which says Frobenius-Poincaré functions actually exist. Okay, so yeah, so I was saying that this can be described by the graded Betti numbers of R mod I power p power n. And so let me just write down the explicit description. So for a fixed n, you can just write down a minimal free resolution of R mod I power p power n as an S module. The minimal free resolution looks like this. So you have the graded Betti numbers B0J till BDJ, where D is the dimension of the ring. Then you can define these quantities called boldface BSJN, where n keeps track of that you are looking at I power bracket p power n. It's just summation, the alternating sum of the graded Betti numbers B alpha J. Sorry, it's not. The alternating sum is over alpha. Then my chi is R power 1 by p power n k e power minus iy by p power n. So which is basically the denominator here. That's basically just a polynomial in e power minus iy by p power n. And the coefficients are given by this boldface bjn. The sum is over j. And note that this is just a polynomial in e power minus iy by p power n. Okay, so now, yeah, so now I'm going to pose another vague question here. So if I look at, again, these modules, these S modules, so consider as S modules. So again, so these are determined by the information of R, the information of I, and the Frobenius. So if I look at the sequence of, if I look at the sequence of modules and its sequence of graded Betti numbers, there should be a pattern in the graded Betti numbers, because again, these are containing a finite amount of information in a sense. So it's determined by the data of R, I, and the Frobenius. And the question is, can we quantify this finiteness explicitly? And this is not just a whim of mind. There are actually results which indicate that yes, there are finiteness in these results. I'll mention one result in this direction and then connect this vague question to my result. Okay, so a result of yeah, so this is a result of Claudia
Alapan.
Yeah.
There's a question in the chat. I don't know if you can see it.
Yeah, I can see it. If I plug in y equal to 0, I get 0 in the denominator. We're supposed to get Hilbert-Kunz multiplicity. That's a very good question. So yeah, so if you plug in y equal to 0, so you get 0 in the denominator. So that, and we already know that this is a holomorphic function that automatically says that if I look at the limiting function, that has a 0 of order d. And yeah, so the Hilbert-Kunz multiplicity is basically the coefficient of iy power d in the power series expansion. Okay. Yeah, so I was talking about a pattern of graded Betti numbers of R mod I power p power n. So, so what does the, so I was going to mention a result. So a theorem due to Miller, Rahmati, and Rebecca Argy. It says the following. So fix, so it says much more, but I will just state the part I need. Fix an odd prime p, and suppose that d is an even integer. So I look at SD. So this is, so what is SD? So these are just the collection of degree d polynomials. So in the polynomial ring in 3 variable, I'm looking at the collection of all degree d polynomials. That's an affine space. There's Zariski topology on that. And so that I can talk about general and very general elements in this space SD. Okay. And what does the result say? The result says that the kx, so call this polynomial ring P. Sorry, this is a bad notation. Call the polynomial ring A. The A module resolution of A mod f x power p power n, y power p power n, z power p power n for very general polynomial f, degree d polynomial f, and in large is as follows. It's A, and then A shifted by minus p power n, reduce sum 3 times. Plus half, and then A reduced sum 3 times, shifted by minus p power n minus d, and last term is A 2d times, so minus 3 by 2 p power n minus half d minus half. Yeah, so the point is that once I fix d, I completely understand the graded free resolution as a function of n. Okay, so this yeah, so this basically gives some content to my speculation that there should be a pattern in the graded Betti numbers. And let's get back to my result, previous result. So in this result, I'm defining a sequence of functions which are built out of the sequence of graded Betti numbers of R mod I power p power n. And my result says that the limiting function is actually holomorphic. It's not some random function. The limiting function limit actually exists, and the limiting function is actually holomorphic. And the way I view at this result is the following. So there is a pattern in the sequence of graded Betti numbers, and that basically ensures the convergence of the sequence and the holomorphicity of the limit. Okay, so yeah, that is one importance of this result. And the other importance comes from something else. So I'll just say it verbally because I'm running out of time. So recently, in 2018, Vijayalakshmi Trivedi defined something called Hilbert-Kunz density functions. So those are continuous functions, continuous functions in the graded setting that generalizes Hilbert-Kunz multiplicity again. And my Frobenius-Poincare functions are actually holomorphic Fourier transform of those Hilbert-Kunz density functions. So there are questions in Hilbert-Kunz density functions which are much more apparent if I take the Fourier transform and if I look at the Frobenius-Poincare functions. And one question about the Hilbert-Kunz density function is the following. The question is, if I take a Hilbert-Kunz density function of a d-dimensional ring, whether it's differentiable d minus 2 times. And that question is completely inaccessible if I just look at the Hilbert-Kunz density function. But if I look at the analogous question in the world of Frobenius-Poincare function, it translates to a question that every commutative algebraist understands. So I write down this question and end my talk with the question. So the question is this. So again, so R, I as before. And suppose that S to R is a graded Noether normalization. So I can look at the following function. So limit as n goes to infinity, chi over S, R mod I power P power n, K, e power minus IY by P power n. So it's basically the function that was appearing in the numerator of the description of the Frobenius-Poincare function. Okay, and my question is the following. So this function is defined for all complex numbers, and I want to know whether if I take this function and restrict on the real line, whether that function is bounded or not. Is this function restricted to the real line bounded? So this is a question that every commutative algebraist should understand. And let me just point out one small thing. So this is a limit of a sequence of functions, right? So these are the sequence of functions. If I fix n, each of these functions are actually bounded. So these are trigonometric polynomials, these are bounded on the real line. So I'm looking at a sequence of bounded functions and asking whether the limit is bounded or not. Yeah, that's the end of my talk. Thank you.
Let's thank Alapan for the nice talk. Any other questions for Alapan?
So in your localization formula, it struck me as interesting that you only have only the minimal primes of minimal height actually matter, which maybe is not so strange since it's something that's really reading things in minimal height. But does that mean that if you're doing this for an ideal that has, minimal primes of different heights, if I just take the minimal part, the minimal height part of that ideal, that it's going to be the same function, or not so much?
Wait, I did try to clarify the question to myself. So there are three parameters here: the module, the ring, and the ideal. So you're taking the ideal, and
I guess I'm thinking of the module being the ideal, right?
Okay.
Yeah.
Sorry. Yeah. So the question is, if I fix the module, then the Frobenius-Poincare function will only see the minimal primes in the support. So you don't see the primes of lower dimension.
So I might as well just So if I replace my ideal with an ideal with just the minimal intersection of the minimal pieces of minimal height, then the function doesn't change.
Wait, I didn't quite understand the question, but
let's say that I is like, you look at all its, its primary components and just take the primary components of the minimal heights.
Right. So
that's what I mean by like the minimal part of it.
Yeah. So you're looking at the module itself, M itself, right? Not the ideal.
Right.
Yeah.
But
so
I'm thinking of the module maybe being R mod I guess. But yeah, because otherwise I don't know how to replace the module for. Right. Oh, but I guess, okay, you could keep the modules fixed and just change the ideal you're doing this with respect to. But no, it's the primes of the ideal that you're thinking about. So So yeah,
No.
I'm thinking of the module being like R mod J.
Yeah, so if you think the mod, yeah, so if you take R mod J, then only the primes of minimal height will matter in this case.
Mhm. Nice. I think there's another question in the chat maybe. Oh, the ideal is supposed to be finite length. Oh, I see. I see. That was maybe a comment just to me. Sorry. It was maybe a partial answer to me that I did not see. I see. Aha. Ah, okay. That makes sense. Mhm. So maybe, oh, I don't know, maybe somebody else has questions. I don't want to hog the.
Go ahead.
Okay, I'll ask my other question.
Mhm.
So you gave us this nice example where you can write what holomorphic function this is, right?
Mhm.
But I'm imagining the answer is no. But is there a shot at there being situations where you can actually compute this Frobenius-Poincaré function without actually knowing the Hilbert-Kunz multiplicity and somehow finding information about finding the Hilbert-Kunz multiplicity from knowing about this function?
That's a good question. Let me see. Yeah, so for example, one case is the two-dimensional. Yeah, so if I look at, say, two-dimensional graded ring, then I'll just go to the page 15 and answer this question. So basically your question is this. So are there examples where the Hilbert-Kunz multiplicity was not known? Then we have computed the Frobenius-Poincaré function, and the Hilbert-Kunz multiplicity has dropped out of it. Yeah, then the strict precise answer to your question is no. But when the ring has dimension 2 and it's graded, it's much easier to compute the Frobenius-Poincaré function, but using the theory of vector bundles on curves. So there are some results of Trivedi and Brenner. So they have computed some objects which has much more information than the Hilbert-Kunz multiplicity, but it's actually easier to compute those objects. Those are finer objects, but it's easier to compute that. And from there, the Hilbert-Kunz multiplicity just pops out. And the same thing happens for Frobenius-Poincaré functions. Yeah. So the way I think about it is it's the following. So I'm throwing in much more information, which makes the object much more rigid. So it forces that, the object has a certain structure, and then I get back the Hilbert-Kunz multiplicity itself.
I see. Thank you. That's great.
Other questions? I'm not seeing any hands or anything in the chat. So the Florian is here, which is nice. All right, well, let's thank Alapan again.